Welcome back. We talked about all three properties of real numbers: algebraic, order, and topological. Now let's talk about some applications. First, some applications on algebraic properties. Let's define subtraction and division first. Adding the additive inverse and multiplying the multiplicative inverse are called the subtraction and division respectively. Also, this y to the negative 1 is the same as 1 over y, and we use both notations. Okay, first let's begin with this one, and this one actually appears in our textbook. Let me find out the page. Yes, this appears in page 7 of Spivak. It goes like this. For any real number x, x times 0 is 0 times x, and it's equal to 0. Well, the first identity is commutativity, so no big deal, but any number times 0 is 0. That's basically it. Now, how do we prove it? It's a bit tricky. Kind of goes like this. Let's begin with x times 0 is equal to x times 0 plus 0 using the property of 0. 0 is the additive identity, so 0 is equal to 0 plus 0. And then let us use the distributivity and break up the parentheses. Now, let's add the additive inverse of x times 0 to both sides. We get that. Because we're adding the additive inverse, the left-hand side is 0. How about the right-hand side? Well, we have to work out a little bit further using the associativity, and we have this grouping, the second grouping, and this grouping will turn out to be 0 again by the additive inverse, so that's 0. And 0 is the additive identity, so it doesn't change anything. Consequently, we end up with the final result. 0 is equal to x times 0. Isn't that what we wanted to prove all along? Yes, it is. So this kind of proof is a little bit higher level compared with the kind of algebraic proof that we saw in the first week, where we begin with, say, tangent of theta, and then just use the definition of tangent, and then algebraically manipulate a little bit, and we have sine of theta over cosine of theta, kind of like that. Those were just left-hand side, the definition, manipulate a little bit, and then we get the right-hand side. This kind of thing is in a little bit higher level because we have to take many different steps. Okay. Let's go over to the next problem. It's about the zero divisor. If x times y is 0, then either x is 0 or y is 0. And this is important because if you solve a quadratic equation, for example, what do you get? Say 2t minus 3 times 3t plus 1 is equal to 0, for example. After factorization we get something like that. And then we use this property to conclude that either the first factor x is 0 or the second factor y is 0. So we get either 2t minus 1 is 2t minus 3 is 0, or 3t plus 1 is 0. Consequently, what we get? T is equal to 3 halves, or t is equals to negative 1/3. We get these kind of solutions, and the justification for this kind of method is presented right here. Keep the right hand side at 0 and factor the left hand side, and set each factor equal to 0. That works for quadratic, cubic, any kind of polynomial equations actually. Why? Well, here comes the justification. So this is important. Okay, how do we prove it? We begin with x times y is equal to 0, and we assume one of them is 0, then the other is, we assume one of them is non-zero, and then the other is 0. Okay, here we go. x times y is 0, and we assume y is not 0. Then, after some steps, it'll turn out x is equal to 0. So one of them has to be 0. Likewise, if x is non-zero, then y will turn out to be 0. How do I do that? Well, let's begin from here. Let's suppose y is non-zero, so multiplicative inverse exists. Multiply by 1 over y to both sides, this one and that one. Right hand side, 0 times y to the negative first power, 0 times a certain real number is 0, and we just proved it in the previous statement here. 3.2a, this one right over here, we just did it. And how about the left hand side? We use the associativity of multiplication, and we end up with y times y inverse, which is 1, resulting in this one. X times 1 is 0, and what is x times 1? It's just x, so we end up with x equals to 0. So if we begin with x times y is 0 and y is non-zero, then x has to be 0. Likewise, you can do the same thing to prove if x is non-zero, then y is 0. Either way, one of them has to be 0, or maybe both is 0. That one's okay. But there's no way you're going to get 0 by multiplying two non-zero numbers. And we proved it like this. Now, can you extend that proof either inductively or repeatedly for something like this? If you have x1 times x2 times x3 times all the way up to xn equals to 0, if you have n factors, then either the first factor is 0, or the second factor is 0, or the third factor is 0, or the last factor is 0. In any case, one of them has to be 0. Yes, you should be able to do that. You can use either repeated application of b, which is kind of naive, or you can use more rigorous approach, use mathematical induction to establish it precisely. I used both actually. Naive description, just applying it repeatedly, just factor like this and that one, and then the second one, factor it again, and then the third one, factor it again, and so on and so forth, and then we get desired result. A little bit too naive. A complete proof is through mathematical induction. Well, the base case is done. And then if you have n numbers, then you can factor like the first number and then the other numbers. Either the first number is 0 or the product of the other numbers are 0. And the red part, you can use the inductive hypothesis because there are this time n minus 1 numbers. By inductive hypothesis, one of them has to be 0, so we get this red part. Conclusion, either the first factor is 0, or the second factor is 0, or the third factor is 0, or the last factor is 0. Let's see, do we have time for some further examples? Looks like we do. Okay, prove the following claims. For any real number, x, negative x is equal to negative 1 times x. Ooh, here comes an interesting problem. We did not define negative x as negative 1 times x, mind you. We defined negative x as the additive inverse of x by proving that there is one and only one additive inverse of x, and we named it as negative x. And this problem is asking you to prove that negative x, which was defined by the additive inverse of x, is the same as negative 1 times x. How do you prove that? Well, you can use uniqueness. If this right hand side satisfies the condition of the additive inverse, then it will be negative x because there's only one additive inverse. In short, x plus negative 1 times x is equal to 0, then everything is true. Well, here it is. We began x plus negative 1 times x. This one. And if that is equal to 0, then we can conclude that negative 1 times x, oh come on, this one satisfies the property, the condition of the additive inverse, and there's only one additive inverse, negative x, so these two have to be the same. Now, how do we prove that the sum is equal to 0? It's not that bad. X plus negative 1 times x, that's where we start. And then please note that x can be written as 1 times x because 1 is the multiplicative identity. And then we use the distributive property backward and factor x out. And inside the parenthesis, we have 1 minus 1. What is 1 minus 1? Negative 1 is the additive inverse of 1. So 1 plus of negative 1, that's 0. We end up with 0 times x. What is 0 times x? It's 0, and that's something we already proved. So we can use it. We proved it, so we can use it. That's how you get x plus negative 1 times x is equal to 0. Consequently, negative 1 times x satisfies the condition of the additive inverse of x. And there is only one additive inverse, which is negative x, so they have to be the same. This is high level. You see, it seems very simple, but this was high level because we used the uniqueness to conclude negative x is equal to negative 1 times x. The second statement is left to the students as an exercise. You can do something very similar to that because what is the right-hand side? This is the additive inverse of x times y. So if you prove that this one satisfies the property, the condition of the additive inverse of xy, then everything will fall into place. So xy plus this number is equal to 0. If you work this out, then this is the same as the unique additive inverse, which is negative x times y. The same for that one. I'm going to leave that as an exercise for you. As a matter of fact, I'm going to require it as a homework. Okay, just enough time for one more. Okay, let's do the next one. For any real number x, negative of negative x is equal to x. Double negative is positive. Yeah, that's something we have been using all the time, but that's not the way we defined the negative. We define negative x or negative y or whatever as the additive inverse. In other words, we have to prove that x is the additive inverse of negative x, because negative of this number is x, so this right hand side x must satisfy the condition of the additive inverse of negative x. How do you do that? I'm going to leave it as an exercise to you. This is required as a homework problem. Once you have that, then you can establish the same thing using the multiplication, and then we're going to end up with this one. Double reciprocal is itself.